Okay, welcome back guys. We're on day 15. This is another example problem from in class. Today we're going to be talking about momentum, and in specific we're going to talk about impulse, which is our normal first discussion of momentum. With this, what we're talking about is we have a few people playing a game of golf. So we've got our golfer all teed up here. We have a golf ball with a mass, so let's put it up here. That's off the board, that's not off the board. A mass of 0.046 kilograms, or 46 grams. That's the weight, the mass of a golf ball. And we have three different golfers, but they're all hitting the golf ball with some force at an angle of 30 degrees. And what they're going to vary is they're going to vary that force, and they're going to vary how long they're in contact with the ball. And for each of them, what we're going to do is we're going to say that time 1 is right before the ball gets hit. Time 2 is right after the ball gets hit, and we want to find the velocity at time 2 for each of the golfers. And then the golf ball is going to fly in some big arc and is going to land on the ground and probably roll, but we're not worrying about that, at some time 3. And we are interested in how far that golf ball goes each time, which is a distance, or what we're going to call it is we're going to call it our position at time 3, assuming that x at 1 and x at 2 are both equal to 0. We're not, technically it's moving as we're applying that force, but these times are small enough that we're going to assume that it's negligible. So we're going to ignore that movement during the impulse. So we've got our initial position for both of these are 0, and it's going to fly and hit the ground somewhere. The first part of this, where we're talking right over in this chunk, we're going to be talking about our impulse, going from 1 to 2, and then going from 2 to 3, we're just getting back to projectile motion, and I'll prove that to you in a second here. So the other pieces that I'm given is I'm given my 3 golfers. So my first golfer, I'm not going to label them 1, 2, and 3 because I have a 1, 2, and 3 already. So I'm going to call them golfer A. And for, how far up do I need to start? We'll see how I do. For golfer A, I have force of golfer A is going to be equal to 2 kilonewtons, which is 2,000 newtons. And they are applying that force for a total of 1 millisecond, 0.001 seconds. And then I'm going to talk about golfer B. Golfer B is going to follow through on the stroke a little bit better. So I have them hitting with a force of golfer B still of 2,000 newtons. And I am then going to have my change in time being how long there's contact for is still going to be 1 millisecond. And then the last piece that I have is golfer C, which when I set it up, it has a force of 1,000 newtons. And only has contact on the ball for a total of 1 millisecond again. What we're going to find is solving each of these 3 is exactly the same. We're just switching out a couple numbers, but it's good practice for us. With that, let's go ahead and write up our what defines. we want the velocity at 2 of golfer A. We want the velocity at 2 of golfer B. We want the velocity at 2 of golfer C. And then we want the distance at 3 of golfer A. We want the distance at 3 of golfer B. We want the distance at 3 of golfer C. So we're going to find all of these values, and we will compare them. Whew. That's the problem. Hopefully I have all of the variables written out there. We're going to go ahead and start with golfer A, and we will start by writing out our impulse equation. So we know that impulse is equal to our change in momentum. And I will tell you that I almost always skip writing this one out. What I would normally write out is impulse. Well, impulse is a force applied over some amount of time. So anytime I have to write my I, I'm normally just going to immediately write force times delta t. And momentum is mass times velocity. So change momentum is mass at 2 times velocity at 2 minus mass at 1 times velocity at 1. In this case, I can actually go ahead and say my masses are not changing, so it's just my velocity changing, and there's my equation. And I can start filling this in by saying that at time 1, I'm not moving. Velocity at 1 is 0. And now if I fill this in for golfer A, I can say that golfer A is providing a total of 2,000 newtons of force. They're applying that force for 0.001 seconds. And that has got to be equal to the mass of my ball, which is 0.046 kilograms, times the velocity of that ball at 2, and since we've had to plug in numbers, we're now talking velocity of A at 2, or velocity 2 of A. Sorry, I switched the order of those. If I multiply these two together, I've got 2 newtons have meters of kilograms, meters per second squared, and we've got units of seconds for our milliseconds. Our seconds are going to go ahead and cancel, so we've got kilograms meters per second. I'm then going to divide through by my 0.046 kilograms, and those kilograms are going to cancel, and I end up with units of meters per second, which is good because we want velocity, and velocity is in meters per second. And I get my velocity of A at time 2 is going to be equal to 43.48 meters per second. So I can go ahead and write that guy up here as 43.48 meters per second. Let me double check since I misspoke. It is 43.48. We're good. Okay. Next step. We have solved to here. Everything from here on out is velocity. So what I did for this one is I ignored that 30 degrees. I said that force is acting in that direction, so the velocity is going to be end up acting in that direction. So it's the same as saying that for this problem, I've got a force acting in this direction, and I want to have my momentum, and I want to have everything set up. This is the positive direction, right where my face is. So that's how I thought about this guy. So my resultant velocity is going to be velocity A2, and if this is 30 degrees, this better be 30 degrees. Okay. Notice that I'm assuming that I don't have any gravity acting that I'm concerned about during that first part. I'm just grabbing that one force for this question. Okay, continuing. We now have to figure out where it lands. This is going back to exam 1, first half of exam 1, first quiz of the semester. We're talking about projectile motion. So what we're going to do is we're going to break everything up into the x and into the y. Now before I get too far ahead of myself, I'm going to go ahead and just prove that this is just projectile motion. I'm going to look at after that impulse. So once this is no longer hitting, the only force on my ball is m times g. And what I'm going to do is I'm going to label positive positive y directions up, positive x directions left and right. I could really throw you guys for a loop, call x up instead. And if I look at this, I can say the sum of my forces in the x is equal to mass times acceleration in the x. I have no forces in the x, which means that if I divide through by my mass, I have no acceleration in the x, which is one of our normal projectile motion pieces, unless we have that wind resistance that I sometimes add on the quiz questions. If I talk about my sum of forces in the y being equal to mass times acceleration in the y, my forces in the y, I have a negative mass times gravity is equal to mass times acceleration in the y. My acceleration in the y is negative g. So my acceleration in the y is negative 9.81 meters per second squared. And at this point, this is what we have set up for most of our, most of the time when we talk about our projectile motion questions, where we're only using our kinematic equations because we have the accelerations. And it's that same acceleration the entire time. Our force isn't changing, our acceleration is not changing. We'll get rid of that, but I am going to go ahead and add a little reminder for myself that this is the positive y-axis and this is the positive x-axis. Okay, first thing we have to do is we have this V2A or VA2, depending on what order I wrote it in, which I didn't hold terribly consistent. I'm going to follow this guy. So I want VA2 in the x, and I want VA2 in the y. Neither of these is just equal to VA2. They're going to have something of 30 degrees on them, and I'll draw that in a second. VA2 times something of 30 degrees. And what that something is, well, let's go ahead and look at it. My velocity is going in this direction. I have a 30-degree angle here. This is my golf ball. I have this guy is the x, so this is VA2 in the x, and this is VA2 in the y. Sure looks like that A2 is going to be, in the x is going to be cosine, and the y is going to be sine. So this is going to be 43.48 meters per second times the cosine of 30 degrees, and this is going to be equal to 43.48 meters per second times the sine of 30 degrees. Well, the reason that I like using 30 degrees is because the sine of 30 degrees is going to be 1/2, which is going to give me a value of 21.78 meters per second. Still not going to divide 43.48 by 2 in my head. And then in the x is a much more ridiculous number, but that gives me a value of 37.65 meters per second. those are my velocities in the x and y at the start. Now the next thing, well, I want x3, so what would my equation for x3 look like? Let's go ahead and write that out, even though we're not actually going to be able to solve it yet. And I'll show you why in a second. A in the x times t squared. Well, a in the x is my acceleration in the x, which we already talked about when we did our forces, is 0. My original position, I say x2 is 0. I want x3, so that's what I want. I have VA2 in the x, so this guy is taken care of. I don't have my time. How am I going to get my time? I'm going to port it over from my y. So we're going to have to solve the y. My y equation is going to look exactly the same, except in order to make things a little bit easier on the math, I'm going to go ahead and solve for y at position 2.5 at this highest moment. And the reason I'm going to do that is because it just makes my math a whole lot simpler. I could go all the way through it, but you guys normally like, I know it's a shortcut to go all the way through it, but you guys like the easier math, and this is much easier math. So in order to do that, what I know about 2.5 is my velocity in the y at 2.5 is going to be 0. Because I'm at my maximum height, I'm going from moving up to moving down. There has to be a point there that it's 0. So v of a in the y at 2.5 is going to be equal to VA in the y at 2 plus my acceleration in the y times my time between 2 and 2.5 seconds. Sorry, not 2 and 2.5 seconds. Time 2 and time 2.5. So velocity in A and the y at 2.5. We chose that because it's going to be 0. Velocity at A in the y at time 2 is going to be a value of 21.78 meters per second. And that is positive because it is going upwards. Positive y is upwards. And we have plus a negative 9.81 meters per second squared. That's negative because gravity is acting downwards, and when I did my force thing, we saw that acceleration in the y is negative g, which is negative 9.8, times this, do I have space for it? I'm just going to put it in as a t. Don't have space for the subscript, I'm sorry. So when I solve this, I subtract this over, divide by negative 9.81, I get a time of from 2 to 2.5 is 2.22 seconds. And what we proved and we talked about, how it always ends up, since we're going from the ground and ending at the ground, our time to get up is the same as our time to get down, so long as the acceleration is constant. And in this case, the acceleration in the y is always that negative 9.81. So I can say the time between 2 and 3 is going to be 4.44 seconds. And that piece is what I'm going to move over this line and use in my x. So with that, x3 then, I now have both of my other pieces. It's going to be velocity of a in the x, which is 37.65 meters per second, times my 4.44 seconds. Seconds and 1 over seconds cancel, and I get a distance that it travels. So I started dropping my a, but this is x3a, so that's this guy that we're solving for. That is going to give me a total value of 166.88 meters. 166.88 meters. Whoop. Wrong spot. I'm used to just going down the list. There we go. And that is the whole solution. Now what we're going to do next is just do it 2 more times. One for golfer B, one for golfer C, and we're going to compare them. But that's the solution. We're just, at this point, we're just going to go ahead and we're going to go into practice mode. Okay. I'll at least fully write it out one more time. Because who knows, maybe I write something slightly differently and you like that second way a little bit better. Okay, golfer B. So I'm going to go ahead and skip writing impulse, and I'm going to write force times delta T. And I'm not now talking about golfer B, is mass, which really isn't changing. So my mass times my velocity at 2 for golfer B, minus my mass times my velocity at 1 for golfer B. Velocity at 1 is 0 because we're starting off before it gets hit. We then have solid contact with it, providing a force from the golf club of 2,000. Okay, I made a mistake. Everything was the same there. 5 milliseconds. So there we go. 5 milliseconds, we have 2,000 newtons for a total of 0.005 seconds is going to be equal to 0.046 kilograms times my velocity. 2b is how I have it written over here. We'll try to match my other stuff. Although this pen is not writing well enough that I think you can read it. I take my 2,000 multiply it by 0.005, divide it by 0.046, and my initial velocity is going to give me a value. Oh! Sorry? I corrected it wrong. Half the contact time. We're not doing better on contact, we're doing worse on contact. This is what your coach doesn't want you doing. Half a millisecond. So 0.0005 seconds, meaning that our velocity, since this is the only piece that changed, is half of our initial velocity, which makes sense. And that velocity of 2 at B is a velocity of 21.74 meters per second. 21.74 meters per second. And I am regretting not using the pink marker for this one. Okay, next piece. We have that velocity. We now are going to start working. Give me a second here. Try to save the marker here. Nope. I apologize. We're still talking about golfer B. I'm using the pink marker. It's not drawing much better. You get these guys alive again. They're brand new markers. That guy looks pretty good. So I have my X, I have my Y. First thing I'm going to do is I am going to say that my acceleration in my X is 0. My acceleration in the y is negative 9.81 meters per second squared. That is just the same, because it's the same free body diagram as it was before. That's just solving that. And then all I have to do is break up my velocity. So velocity of 2 at b in the x is going to be 21.74 meters per second times something. And in this case, that something is going to be cosine, just like it was before, of 30 degrees. And that gives me a value of 18.83 meters per second. And then my velocity of 2 at b in the y is going to be 21.74 meters per second times the sine in the y of 30 degrees. And that is going to give me a value in the y. Well, that's just half. That's 10.87 meters per second in the y. Going a little bit faster this time, because we already did the same thing once. And then what I'm going to do after this is I'm going to go ahead and say that I have my, we learned our lesson, we're going to solve y first. So we're going to say that velocity at 2.5 for b in the y is going to be my velocity at 2 at b in the y plus my acceleration in the y times the time between 2 and 2.5. Again, we're jumping to the top from here instead of going all the way to 3 because this top point by definition is 0, and this 2 at b in the y is that 10.78 that we had before. My acceleration, we can possibly fit it, is negative 9.81 meters per second squared times my time between 2 and 2.5. You'll have to trust me, there's a 0.5 after that. And that means that my time between 2 and 2.5, in this case, it is 1.11 seconds, meaning that my time from 2 to 3 better be 2.22 seconds. And I can move that back over here, and I can solve my x. X at 3 for golfer B is going to be x at 2 for golfer B plus my velocity in the x at 2 for B times my time between 2 and 3 plus 1/2 times my acceleration in the x times my time squared between 2 and 3. Hoofda, I fit it. Acceleration in the x is 0. Position at 2 in the x is 0. X, 3 in the b, I've got the same naming convention as I have right there, is going to be equal to my velocity, which is 18.83 meters per second, times my time, which is 2.22 seconds. And that is going to give me a total value of 41.72 meters. And we will try to write that in blue up here. 41.72 meters. Oofda. that is a quarter. So we halved the time that we had contact on the ball, and it went a quarter of the distance. That is a great drive. That is a not so great drive. So half a millisecond cost us 125 meters of distance for that drive. So follow through. Okay, what about if we half the force? And I will write it all out, or I'll write the first half out and we'll realize that we already have the numbers, but give me a second here. Okay, last one, we're almost there. So we have our force times our change in time is equal to mass times velocity at 2 minus mass times velocity at 1. My velocity at 1 is 0. My force is going to be, in this case, 1,000 newtons. My time is going to be 0.001 seconds. That is going to be 0.046 kilograms times my velocity at 2. If I solve for this, my velocity at 2 is going to be 21.74 meters per second. Well, this guy and this guy are exactly the same. My velocity for 2 in the B, for golfer B, and velocity at 2 for golfer C. And hopefully that means to you that my distance is going to be the same. Because if we look at how we solved that whole second half of the problem, nothing changed. Nothing was dependent on either force or time for that entire piece of ball. Delta time, time of impact. Nothing was dependent upon that in the second half of our solution in this whole kinematic equation. There was a time, but that was a different time. That was the time between here and here, not the time between 1 and 2. Time between 1 and 2 never showed up, which means that this x3 in C is going to end up being 41.72 meters. So we could either double the force that we put on something to make it go the same, to make it go 4 times as far, or we can or we can double the time that is in contact. And the reason we talk about following through on your stroke is it's a whole lot easier to just keep contact for twice as long as it is to follow through on your stroke than it is to provide twice as much force on the hit. So that is why following through in baseball, in racquetball, in tennis, in golf, in soccer, you follow through with your hit, your kick, whatever it is. And that's impulse. Now, I will, you guys can always not watch it. So I will go ahead and go through and solve this super fast. So I've got X and I've got Y. Velocity of 2 for C in the X is going to be velocity 2 for C, 21.74 meters per second times the cosine of 30 degrees. That is going to give me a value of 18.83 meters per second. Velocity 2 for C and the Y is 21.74 times the sine of 30 degrees, which is going to be equal to 10.87 meters per second. If I say that my velocity final, my velocity at 2.5 is 0. I then say 0 is equal to 10.87 because we've got initial velocity up minus 9.81 meters per second squared times my time between 2 and 2.5. My time between 2 and 2.5 becomes 1.11 seconds. My time then to get all the way back down to the ground is double that, so time between 2 and 3 is going to be equal to 2.22 seconds. I can then say that my x at time 3, which is what I'm going to solve for, is going to be my initial position, which is 0, that's x at 2, plus my velocity at 2, which is 18.83 meters per second in the x, times my time, which is 2.22 seconds, plus 1/2 times my acceleration times my time squared. My acceleration is 0, so that's 0. And I get a total value of 41.72 meters. 41.72 meters. Wrote a whole lot less down there, but hopefully it's still fairly straightforward. That is our example problem. See you next time.